So the topic we're going to look at today is global state collection. In a distributed system that consists of many processes, each of these processes executes actions on the basis of local information as well as global information that is available. So there are several applications for which we need to find out the global state of the entire system or the states of all the processes in the system, um, and the processes in the system need to collect the local states of all the processes and stitch them together in order to get the global state of the entire system. So the global state collection is an extension of the global snapshot that we looked at in the previous lecture. There we were collecting only the fragmented local states, and each of the processes were recording only their local states. But in this lecture we are going to look at processes trying to collect an overall state of the entire system. Now let's look at some of the applications of global state collection in the real life scenarios. So some of them include computing network topology, and then the other two applications which are listed here in the slide are termination detection and deadlock detection. So the last two applications were also listed when we looked at the previous lecture about collecting the global snapshot. So why do we need termination detection? So let's look at an example of algorithms. So most algorithms run in different phases. Okay, so after the completion of phase 1, the algorithm moves on to phase 2. So how do we know that the phase 1 has completed and we have to move on to phase 2 of the algorithm? So this is where we need to detect that the phase 1 of the algorithm has terminated, and hence we can move on to the phase 2 of the algorithm. So this is an important application to run almost about any algorithm in a distributed system. Deadlock detection is also a branch that comes out of termination detection. So basically, in order to find out whether the algorithm is kind of stuck looping at a certain point or has it terminated with a final legal state, we need to know the global state of the entire system. Now, as indicated in the slide, we can see that Shandy-Lamport algorithm does only a partial job of finding the global state of all the processes in the system. So basically the distributed snapshot algorithm, which was the Shandy-Lamport algorithm that we read about in the previous lecture, it only clarifies the notion of the existence of a consistent global state, right? And then it goes ahead and helps to record the fragments of this global state locally in each of the processes. However, why do we say this algorithm is doing a partial job? The reason is it does not address the task of collecting all these fragments and stitching them together to give a one common global state of the entire system, or one common view of the global state of the entire system. So in this lecture, as we move forward, we're going to look at algorithms to find the global state of the entire system. That is, each process is going to discover the global state of the all the processes in the system, and then we're going to go ahead and do some algorithms for termination detection and also for deadlock detection. So once again, let's look at the at a simple exercise of collecting the global state of all the processes. So to begin, let's go back and remember how we recorded the local state of each of the processes in while collecting the global snapshot. So on the right side, we see a picture with four processes, I, J, K, and L, and they have a recorded states, okay, recorded consistent states, S of I, S of J, S of K, and S of L at each of these processes in accordance with the global snapshot algorithm. Okay, now moving ahead, we are going to look at how to stitch them together to form a single global uh, state, okay, which consists of all the states of all these processes. Okay, so basically what we're going to do is we're going to use an algorithm for all-to-all broadcast, okay, where every process broadcasts its state to every other process in the system, so that every process can learn the state of every process in the system. So for doing that, we use the all-to-all broadcast mechanism, and the end of, of this all-to-all broadcast algorithm, every process ends up with a set of states, which is the set of states of all the processes corresponding to all the processes in the system. Okay, so the V is the set of states, which is S of I, that corresponds to each and every process in the distributed system. So in the following slide, we are going to take a more closer look at the all-to-all broadcast algorithm and the assumptions we make for the algorithm. So the all-to-all broadcast algorithm is given in the slide. So before we look at the algorithm, let's look at the assumption made in this algorithm. So we assume that the topology being considered is a strongly connected graph. What that means is every process is connected to every other process in the system. Alright, so that is the meaning of a strongly connected graph. Now, after the assumption, let's move on to the algorithm. So the program is called broadcast, and this is the program or the computation that is done at each process in order to collect the global states of all the other processes. So there are two sets which are associated with each process, or each process maintains two sets. So let's look at what those sets are. The first one is called V sub I, and the other one is called W sub I. Okay, so the set V is going to denote the current set of values that have been collected so far, all right, and the set W sub I is going to represent the last or the latest value of VI that was sent along the outgoing channels so far. Now the initial values of Vi is nothing but its local state, because that's the only state that the process I has knowledge of before it starts the all-to-all broadcast algorithm. And Wi is empty because nothing has been sent over the outgoing channel yet. All right, nothing has been shared with the other processes yet. So once again, Vi is the set of current values collected so far, and Wi the latest set of values of Vi that was sent along the outgoing channels. So initially, before starting the algorithm, Vi only consists of the local state Si of that particular process I, and the value and the set Wi is empty before the algorithm is started. Now let's take a look at the two statements in the algorithm. So the very first statement indicates that if Vi and Wi are not equal, okay, so if it received a new state and the value of Vi had changed, okay, so a new state has been added to Vi, then it also has to be sent out on the outgoing channel and shared with all the other processes. All right, so when Vi becomes not equal to Wi, then we're going to send the latest Vi on every outgoing channel, and we're going to update Wi to the latest values of Vi. All right, so whenever a new state is received, the value of Vi changes. Okay, so we're going to send the new value of Vi out on the outgoing channel, and we are going to update the set Wi to the latest values which are in Vi. Now let's take a look at the second statement in the program. So it says that if the channel k comma I is not empty, okay, so that means it is going to receive a new state value along the channel. Then you receive that state value along the channel, okay, ki, I'm sorry, and then we're going to add that state to the existing set of states that we have collected in Vi so far. Okay, so whenever the receiving channel to the state to the process is not empty, that means we are receiving a new value or a new state value which we are going to collect and add to our set of states Vi. So as soon as we receive this, uh, uh, the the first statement is going to become true in the next iteration because we have added a new state to Vi. Vi is going to become not equal to Wi, and so we'll have to send the new state that we have collected over once again over the outgoing channel. Okay, so basically we are collecting new states over our incoming channel and updating the value of Vi and sending the new set of states in Vi over the outgoing channel. So this is a continuous process that is going to continue. Let's look at when the algorithm will terminate. So the algorithm is going to terminate when both of the guards in the given program become false, right? So when both of the guards become false. So what are the guards here? The guards are when Vi is not equal to Wi, right? And when the channel is not empty. So when both of them become false, what does that mean? That means then the Vi value should be equal to Wi, all right, and all the channels should be empty. Okay, so the algorithm will terminate when no process receives any new value, and thus the set Vi remains unchanged, and so it will always be equal to Wi, and also when every channel in the system is empty. Moving forward, we're going to look at some of the lemmas associated with this algorithm. As I mentioned, since your final exam is going to be a multiple choice exam, we are not going to focus too much on the proofs associated with the algorithm, all right, with the lemmas. Instead, we are just going to look at the proof outline to get a basic understanding of the lemma itself. So let's take a look at lemma 1. So what does the lemma 1 mean? So let's assume there are two processes I and K. all right, and there is a directed edge from process I to process K, all right, then if the channel IK is empty, okay, so if the edge going from process I to process K, or the channel going from process I to process K is empty, it implies that the W set associated with the process I is a subset or equal to the V set associated with the process K. So the proof of this lemma is done on by using the induction, by using mathematical induction. So to give a very basic idea, initially the W of I is going to be empty, all right, and V of I was S of I. Those were the initial states, sets that we started with, as shown in the algorithm in the previous slide. So in the initial state, your Wi is a subset or equal to Vk, all right, and it holds. Then an assumption is made using the induction hypothesis that Wi being a subset or equal to Vk is going to hold after the process I executes the first statement R times, and basically the proof goes on ahead to prove that it will also hold in the R plus 1th step. Okay, so this is just to give a basic idea of how it has been proved. So in simple words, it uses mathematical induction to prove the lemma 1 listed on the slide. Okay, moving on the slide, what we are trying to show is that the set of states collected by all the processes is consistent, okay, or the same, all right. So in order to prove that, we make use of the termination condition for the algorithm, for the all-to-all broadcast algorithm, okay. So the termination condition for the algorithm was that the value of Vi should become equal to Wi, right, and all the channels are empty. Okay, so that's when both the guards or both the uh, guards for both the statements become false, and hence the program will terminate, right? So Vi is equal to Wi. Wi is a condition for the program to terminate, all right? Now using the lemma listed on the very first line on the slide, okay, since Vi is equal to Wi, we also get that Vi is a subset of or equal to Vk. Okay, so we are trying to replace the Wi in the lemma with Vi because of the termination condition. All right, so Vi is also a subset or equal to Vk. Okay, now moving on. Now let's go back to the assumption we made for the algorithm. So the first assumption we made for the algorithm was the graph we are looking at is a strongly connected graph. So every process is connected to other process, all right. So in the figure on the right hand side on the slide, there are two processes, I and K, right? So if there is a path from I to K, there is also a path from K to I, all right. So that is what a strongly connected graph means. And so there will always be a cycle between any two processes I and K. Okay, so that's what it says. In a strongly connected graph, every node is in a cycle with every other node in the system. Okay, so on a cyclic path, V of I equals V of K must be true. Now how do we get that? So in the previous statement we got V of I is a subset or equal to V of K, right? Since there is a path from I to K, all right. Now we also know that there is a cycle here, and so there is a path from K to I as well. So V of k is also a subset or equal to v of I. Okay, so from these two statements together, since v of I is a subset equal to v of k and v of k is a subset of equal to v of I, we get v of I should be equal to v of k. Right, when two sets are basically have a subset or equal to relationship with each other, all right, both ways, then they become equal. Okay, so then they are the same set. And so from this we get the fact that if S of I belongs to V of I, S of I will also belong to V of k. Or another way of putting it is, if S of k belongs to V of k, S of k will also belong to V of I. So all the sets in V of I, all the states in V of I will also be in V of k. So this shows that the global state collect after the termination of the algorithm consists of the same set of states at each of the processes. Now let's look at the next lemma. So this lemma says that the algorithm, the all-to-all broadcast algorithm, is going to terminate in a bounded number of steps or a finite number of steps, right? So in order to this, let's consider a variant function y, right, which consists of all the sets v0, v1, so on till vn minus 1 associated with each of the processes processes 0, 1, 2, so on till n minus 1. And then it also consists of all the channel states, okay, of all the m channels in the network. So initially, like we looked at in the algorithm, so each of the sets v0, v1, v2, so on till vn minus 1 is only going to contain their local state. So v0 will contain the state s0, v1 will contain the state s1, v2 will contain the state s2, and so on till vn minus 1 is going to contain the state sn minus 1. All right, and nothing has been sent on the channels yet, so each of the channel states is going to be empty. So as the algorithm proceeds and statement 1 and statement 2 of the algorithm are executed one after another, so the channel state continuously changes as new states are sent over the channels and received over the channels by different processes, and the V sets also increase in size as they gather the state information of the other processes in the system. So eventually, each of the V sets associated with the processes are going to reach their largest value, which consists of the states associated with all the processes in the system, S0, S1, S2, so on till Sn minus 1. So each of the V's is going to contain the same set of states, S0 to Sn minus 1. Since the number of processes in the system is finite, it is going to take a finite number of steps in order to collect all these states. All right, so this is the premise used for proving this lemma, and hence the algorithm is going to terminate in a finite amount of time, or it's going to terminate in bounded number of steps. So the next topic we're going to look at in this lecture is termination detection. So basically, we're going to look at an algorithm to detect whether the termination or the final state has been reached. Okay, so during the progress of a computation in a distributed system, there are several processes in the distributed system, and in order to find out whether it has terminated or not, this task is delegated from one process to another process, and the processes turn active or passive periodically. So let's look at the conditions which which would prove the of a termination of a computation in a distributed system. Okay, so the first condition that has to be met is every process in the system must become passive. Okay, so every process in the system must become passive, and then not only that, all the channels in the distributed system should become empty. Okay, because if there is something along the channel, then a process becoming active again is a possibility, right? We don't want that to happen, and so that's how uh, part B is also related to condition B is also related to condition A. So every process has to become passive and all the channels have to be empty. And then finally, the last condition is that the global state that has been reached in the computation should satisfy the desired post condition. Okay, so the third condition C here is the most important one, which separates the termination state from a deadlock state. Okay, so this is the main difference between termination and a deadlock. So in a deadlock, we're going to be stuck in a cycle and it is not never going to reach a legal final state. Okay, it is never going to meet a desired post condition. Okay, however, in termination, a global state has to satisfy the desired post condition. Moving on, in the next slide, we're going to take a look at how a diffusing computation takes place and how different processes instigate each other to find out whether a termination has occurred or not. So now let's look at how the processes engage in diffusing computation in order to find out whether the termination condition has been met and the computation has terminated or not. Okay, so let's look at about 5 processes in the system: process 1, 2, 3, 4, and 5. So in figure A, we see that the process 1 actually initiates the algorithm to find out whether the termination has occurred or not. Okay, so the process 1 is called the initiator process or the initiator node. Okay, so the process 1 engages process 2 uh, and to find out about the termination situation. So another thing we notice in all the figures is that the black process is the process are the processes which are currently active, and the white processes are the passive processes. Okay, so initially in the first figure A, the process 1 is active and it has engaged process 2, and process 2 also becomes active and it has turned black. Okay, and in figure B, we notice that the process 1, after engaging process 2, it has gone back into passive state. It has turned white. All right. On the other hand, the process 2 is engaging process 3, okay, to find out about the termination, and so process 3 has become active as well. All right. So in the second figure, both process 2 and process 3 are involved, are actively involved, and so they're both in active states. The remaining processes 1, 4, and 5 are in the passive state. Now moving on to the third figure, figure C on the slide. So what has happened through pictures A, B, and C is that 1 had engaged 2, made 2 active, and 1 had turned passive, right? 2 engaged 3, right? 2 became passive, and then 3 became active. 3 engaged the process 4, all right? 3 remained active, and then 4 engaged 5, and then it became passive. Even after 4 became passive, 3 continued to remain active. And now finally the process 5 is trying to engage process 2 in the algorithm. Okay, so finally in the figure C, we notice that processes 3 and 5 are active, where processes 1, 2, and 4 have become passive. So the processes move from active to passive state, all right, and engage other processes while transmitting signals, or basically they use a signaling mechanism in order to detect whether the termination has occurred yet or not. So this diffusing computation forms the basis for the algorithm that we're going to look at in the next slide, which is called the Dijkstra-Scholten algorithm for termination detection. Let's look at the basic scheme behind the Dijkstra-Scholten algorithm. So the very first thing we need to know is that the algorithm is started by a node called the initiator node, or the initiator process, which actually initiates the termination detection algorithm by sending signals or messages down the edges via which it engages other nodes. All right, on the right hand side, the very first picture shows node J engaging node K and sending signals from J to K, by sending signals from J to K in order to detect the termination. Okay, and um, at a suitable time, all right, at a suitable time we'll find out what the suitable time is. Okay, the recipient of the message or the signal will send back an acknowledgement to the sender. Okay, so whenever the initiator of the signaling mechanism receives an acknowledgement along every node that it sent a signal out on, all right, or every node that it had engaged, that is when it did termination. Okay, so in simple words, an initiator process starts the termination detection process, or the signaling mechanism, and sends out signals or messages along outgoing nodes, all right, and it engages all the processes which are connected to it along outgoing channels. Okay, and whenever the outgoing channels think it is the right time to send back acknowledgement, they would acknowledge the signal received to the sender. Okay, when the sender process receives all the acknowledgements along all the channels that it had sent out signals on, that is when it is going to assume that termination has occurred, or basically it detects termination. On the right hand side, we see the second picture shows J sending out a signal to process K, all right, and the third picture shows the process K sending an acknowledgement back to the process J. Now let's take a deeper look at the terminology associated with the Dijkstra-Scholten algorithm. Okay, in order to understand the algorithm, we need to understand some of the terms. The first one is called deficit. Okay, so there is a deficit associated with each edge E in the distributed system. Okay, so the deficit along an edge E is nothing but the number of signals on edge E minus the number of acknowledgements that are received along the edge E. Okay, so for any edge E in the distributed system of processes, so the number of signals that were sent via the edge minus the number of acknowledgements that were sent back on the same edge gives the deficit on that edge. Okay, now we also separate out the um, deficit values along the incoming as well as the outgoing edges. So for a given node or for given process, okay, so the letter C depicts the total deficit along all its incoming edges, okay, and the letter D indicates the total deficit along all the outgoing edges. Okay, so for example, the process 1, if you consider process 1, right, and the edge along 0 to 1, okay, the edge along 0 to 1 indicates the deficit C for the process 1, okay, and the for the same process 1, D is indicated by the deficit along the edge 1, 2 and the edge 1, 3, because both of them are the outgoing edges. All right, so 0, 1 edge gives the value of the deficit C, which is the total deficit along the incoming edges for the node 1. This is for node 1, okay, and then the total deficit along edge 1, 2 and 1, 3 is given by D, which is the total deficit along the outgoing edges. Once again, this is for the process 1. So it's very apparent that the initiator process, or the process which actually initiates or starts the termination detection algorithm, uh, only has outgoing edges. It does not have any incoming edges, and so by definition the value of C, which is the total deficit along incoming edges, is going to be equal to 0, because of course it has no incoming edges incident of it. So in the figure on the right hand side, 0 is the initiator process. It has no incoming edges coming into 0, right? And so the value of C is going to be 0 for the process 0. Now the Dijkstra-Scholten algorithm uses two invariants to develop the algorithm. Okay, so if you remember from a long time back, what is an invariant? An invariant is something which is true at all times, before the computation of a program, during the computation of a program, and after the computation of a program. All right, so an invariant is a condition, or it's something which is always true. Okay, so we have two invariants associated with the Dijkstra-Scholten algorithm, which basically help develop or design the Dijkstra-Scholten algorithm. So let's take a look at the two invariants. So the first invariant is very straightforward. It, um, it comes from the fact that the deficits are always non-negative integers, even if they are incoming along incoming edges or along outgoing edges. Okay, so basically no node is going to send out an acknowledgement before receiving a signal. All right. So the number of signals sent out is always going to be uh, greater than the greater or equal to number of acknowledgements received. The number of acknowledgement received along an edge is never going to exceed the number of signals that were sent along that edge. Okay, and that is why we have the value of C is always greater than equal to 0, and the value of D is always greater than equal to 0. So the deficit along either an incoming edge or along an outgoing edge is always going to be a non-negative integer. And that's how we get the first invariant. Let's take a look at the second invariant. So initially for every node, the value of C is going to be equal to 0 and the value of D is going to be equal to 0. Okay. The initiator node initiates the computation by sending a message to each of its successors. All right. So to each of the nodes on its outgoing edges. All right. So um, for that node or for the initiator node, the value of C is going to be equal to 0 and D is going to be equal to K. For every other node in the system, that means for every internal node in the system, the second invariant has to be preserved. Okay, so the second invariant says that C is greater than 0 or D is equal to 0. So the second invariant simply means that the C is greater than 0. That means the deficit along incoming edges is greater than 0. Okay, so unless messages are received along the incoming edges, they won't be sent along the outgoing edges, right? So they both mean the same thing. So when we receive so initially when we receive messages along the incoming edges, the value of D is 0 since nothing is sent out yet along the outgoing edge. The value of D is 0. In the following slide, we're going to look at how the invariants are going to hold when for an internal node when an acknowledgement is received. Okay, so the invariant 2 is the cornerstone of the proposed algorithm. An internal node is going to send out signal only after it receives a signal from its previous node. All right, so this increases the D for the sender, but it does not affect the invariant 2 as long as C is greater than 0. The sending of an acknowledgement reduces the sender's deficit or the value of C by 1. So in order to preserve both invariant 1 and 2, an acknowledgement is sent when the condition given in the slide holds. Okay, so C minus 1 should be greater than equal to 0 and C minus 1 is greater than 0 or D equals 0. So we get this from both invariant 1 and invariant 2. Now we're going to go ahead and use some of the discrete mathematics and uh, the expand the above um, expand the above and finally we're going to end up with C greater than 1 or C equals to 1 and D is equal to 0. So this implies that an internal node returns an acknowledgement when the value of C exceeds 1 or when the value of C equals to 1 and the value of D is equal to 0. That is, it has received acknowledgement from each of the nodes that it had sent out signals or messages on. Now let's move on and take a look at the actual algorithm that describes the pseudocode of the algorithm for Dijkstra-Scholten algorithm. Now let's take a careful look at the Dijkstra-Scholten algorithm. Okay, so this slide presents the program for the Dijkstra-Scholten algorithm. It's called detect, and this is the program which is implemented at each of the processes individually. Okay, so initially each of the processes has the following value set. Okay, so the value of C, that is deficit along incoming edges, is equal to 0. The value of D, that is the deficit along the outgoing edges, is 0, and the parent is set to itself. So every node has the parent value set to itself. Okay, so these are the initial variables that are set in each of the processes. Now let's look at each of the statements of the Dijkstra-Scholten algorithm. So in the very first statement, we see that if a signal is received, okay, so if a message M or a signal is received and the value of C is equal to is equal to 0, which means that this is the very first signal that was received by a process I. Okay, this is the very first time a signal was received by the process I. So what does the process do? It's going to do the following. It's going to set its value of C to 1. Okay, so deficit along incoming edge to 1. It's going to make itself active. It's going to set its state to active, and then it's going to make its parent as the sender of the message or the signal. Okay, following that, the process I is also going to engage all the nodes along its outgoing edges. All right, and then finally it's going to turn passive. All right, so that is the first statement in this algorithm. Now let's look at the second statement in the algorithm. If the message received is an acknowledgement, okay, so it had sent out when it had sent out the signal along its outgoing edges, it is going to receive acknowledgement at some point of time, right? So when it receives an acknowledgement along its outgoing edges, what is going to happen is it has to decrease its deficit along the outgoing edges by 1, right? So it's going to decrease the value of D by 1. So that's what happens in the second statement of the algorithm. Now let's look at the third statement in the algorithm. In the third statement, we see that if C equals 1 and D equals 0, okay, and the state is equal to passive. All right, so the value of C equals 1. What does that mean? It means that it had the process I had already received a message along another incoming edge. Okay, along another incoming edge, it had already received a message. Okay, and it basically sent out the message along all the outgoing edges and had turned itself passive. All right, and that's why the value of state is equal to passive, and the value of D equals 0. Okay, so this means that it has 0 deficit along the outgoing edges, so it has received all the acknowledgements it's expecting. Okay, so what it's going to do is, now since it has received all the acknowledgements, okay, and it had already received this message on another incoming edge, it's going to send an acknowledgement to the parent. Okay, reset the value of C to 0, and then it's going to reset the value of the parent variable to itself. So basically what is the process doing? It's going back to its initial state. All right, so the initial state where it started with c equals 0, d equals 0, parent equals to I. So it's actually resetting itself to the initial state. Now let's look at the fourth statement in the algorithm. If a signal is received and the value of c equals 1, then you're just simply going to send an acknowledgement back to the sender. You're not going to make the sender your parent. Okay, that is done in the first statement that we looked at. Okay, since the difference between the first and the fourth statements in the algorithm is the value of c. Okay, so if this is the first message that is received, it is the first time that it received a signal, then it's going to set the sender as its parent. But if the value of c equals 1, that means it had already received a signal along that incoming edge, then it's going to simply just acknowledge the sender. It's going to simply send an acknowledgement to the sender. It is not going to set the sender as its parent. Okay. So that is what is given in the very last statement in this algorithm. The note that indicates that the parent relation basically induces a spanning tree. Okay, since every node does not acknowledge every sender as its parent. Okay, that makes sure that there is a spanning tree which is developed in order to detect the termination in the algorithm. Okay, so this is the end of the Dijkstra-Scholten algorithm for termination detection. The next thing we're going to look at is distributed deadlock and deadlock detecting algorithms. So now let's take a look at distributed deadlock. So in a distributed system with a set of processes, a set of processes is considered to be deadlocked when the computation reaches some global state which is different from the desired goal state, okay, or which is different from the desired final state. All right, and every process is waiting for some other process to execute an action, and basically ends up in a condition which is never going to be satisfied. So in simple words, when every process is waiting for some other process in the system in order to execute an action or for a computation, a deadlock occurs. So we are going to assume that every process owns a couple of resources, okay? And we're going to take a look at how these resources are allocated and how these resource allocation ends up in a condition called deadlock. So there are three main criteria or reasons why a deadlock can happen in a distributed system. So the very first reason is exclusive use of resources, or um, another term to describe that is mutual exclusion. Okay, so we have looked at mutual exclusion time and again since the beginning of the semester. Okay, so when there is a resource which can only be used by a single process at a given point of time, it could result, or it could be a reason why a deadlock could happen when one process is waiting on another process and another process is waiting on this one process to enter a critical section. So when these resources have to be used only exclusively, that is one of the reasons for a deadlock to happen. Now the other reason why a deadlock can occur is preemptive scheduling. Okay, so what does non-preemptive scheduling? What does it mean by by non-preemptive resource scheduling. That is, when a process gets access to a certain set of resources, if you cannot uh, stop the process in the middle and take back the resources, that is called non-preemptive scheduling. Okay, so when a resource gets allocated to a process, it is not going to be freed unless the process wishes to. So that kind of a scenario also leads to a deadlock. Okay, so that is called non-preemptive scheduling. Now the last one is something that we looked at very recently, where there is a subset of processes. Okay, let's say there are process 1, 2, 3, and 4. Processes 1 is waiting for 2, process 2 is waiting for 3, process 3 is waiting for 4, and the process 4 in turn is waiting on process 1. Okay, so this results in a circular waiting of all the processes, which results in a distributed deadlock. So these are the three criteria or three cases or three reasons why a deadlock can occur in a distributed system. Now moving on, let's look at how a deadlock can be handled in a distributed system of processes. Okay, so there are three aspects of deadlock. So there are three ways in which deadlock can be handled. The first one is deadlock detection, the second is deadlock prevention, and the third one is deadlock recovery. So the first thing is we have to detect a deadlock. A deadlock has happened, all right. So that is why, so that it is not confused with a termination condition, all right. So we have to differentiate the deadlock from a termination and basically discover or detect that a deadlock has actually happened. Okay. Now moving on, once the deadlock is detected, it has we have to come out of the deadlock. So we have to do something or some computation or some process in order for the processes involved in the deadlock to recover from the deadlock situation. So that is the process of deadlock recovery. Now, other than these two, it is possible to prevent the deadlock in the first place. Okay, so we can make sure that the deadlock never happens. In order to do that, it could be more expensive to prevent the deadlock the in most algorithms, and we'll look at the reason why deadlock detection and recovery are more favorable than the deadlock prevention process. So we looked at different ways of dealing with a distributed deadlock. So the reason why a deadlock could occur is a bad design of an algorithm or a bad strategy which was taken into account while developing an algorithm. Okay. Now sometimes the prevention of a deadlock is more expensive than detection of the deadlock and recovery from the deadlock. So most of the design of the distributed algorithms may not care about deadlocks at all, because it could be a very rare scenario. So if the deadlock doesn't happen very often, having an algorithm to detect to prevent deadlock at all times could be an expensive process. And that is why just detecting a deadlock in case of timeout and recovering from the deadlock is more suitable uh, is a more suitable way of recovering from the deadlock than uh, having an algorithm to prevent it in the first place. So the main reasons for failures for deadlock are failures or perturbations in the distributed system. So the best way to represent a deadlock is using a wait for graph. A wait for graph is nothing but a representation of different processes and showing which process is waiting for which process. All right. So in practice, a single process cannot see the entire wait for graph. It only has a set of processes that it is waiting for. Okay, so this is in case if there is a central coordinator, or just for us to look at and understand the actual deadlock situation. Okay, so a single process does not have the access to this wait for graph. All right, so in the figure given on the right hand side, we see a wait for graph where the process P naught is waiting for process P1. Process P1 is waiting on process P4. Okay, process P4 is waiting on process P2. Process P2 is waiting on both processes P0 and process P1. Process P3 is waiting on process P1. So when there is an edge from process I to process J, that means the process I is waiting on process J. Okay, so you that is how you show who is waiting for whom in the wait for graph. Now let's take a look. Let's take a look at the different kinds of deadlocks that exist. So the first one is called the resource deadlock, and the second kind is called the communication deadlock. Okay, so let's look at what resource deadlock is. When a process is waiting on resources, multiple resources from various other processes, and it needs all these resources in order to make progress or in order to proceed, it is called a resource deadlock. Okay, since the waiting process needs each and every one of these resources in order to proceed, it is also known as the and deadlock, where each of these processes, all these processes are required in order to proceed. The other kind of deadlock is called communication deadlock, when a process is dependent on a set of processes in order to proceed. That is, if any one process in the dependent set, gives an OK, the waiting process can proceed. That is called a communication deadlock. Okay, since it's waiting on at least one of the processes from the dependent set to give it an OK to proceed, it is also known as the OR deadlock. Okay, so the names given for the resource deadlock and communication deadlock are AND deadlock and OR deadlock respectively. Okay, now let's look at some of the terminology or notations required to understand the algorithm for detection of resource deadlock. Okay, so the first one on the slide is W of J, okay, is equal to true. This implies that J is in a waiting state. Okay, so if a process J is in a waiting state, then the W of J value of that particular process J is going to be true. Now moving on, let's look at the second notation. Depend of J comma I equals true. Alright, this implies that J is one of the successors of I. Alright, that means there is an edge from I to J. Alright, so basically I's progress depends on J's progress. So another way to put it is J is holding on to a resource which I needs. Okay, so once J proceeds and let's go of the resource that I is looking for, I can also proceed. So basically depend of J comma I means I's progress depends on J's progress. Okay, now let's look at the third notation, which is P of I comma S comma K. So P of I comma S comma K is a probe. Okay, so a probe that is sent from the initiator process. So the I stands for the initiator process, S stands for the process that is sending the probe out, and R is the receiver of the probe. So on the in the figure on the right hand side, we see a probe being sent from process 4 to process 3. So the process 4 is also the initiator of the probe. So the I value is 4, and it's also the sender of the probe. So the S value is 4 and it's sending it to the process 3. Okay, so the K value is 3. Now, if this probe were being sent from process 3 to process 2, the probe value would be P of the initiator is going to remain as 4, the sender is going to become 3, and the receiver is going to become 2. So the probe value is going to be 4, 3, 2 if this were a probe being sent from process 3 to process 2. Now let's move on and take a look at the detection algorithm for a resource deadlock. Now let's take a look at the detection algorithm for a resource deadlock. So this is the algorithm that is executed by each of the processes to detect a resource deadlock. Okay, so let's say a process K is executing this program. Okay, there are two guard statements or two statements associated with the program. So the first statement of the program uh, looks at a couple of conditions. So the first condition is the value of P of I comma S comma K, which is received. So the probe that is received is true if the value of P of I comma S comma K is received on an incoming node, right? So if a probe is received on an incoming node, that is the first condition that has to be true. Now let's look at the second condition. So W of K is true. So K is in a waiting state. So the process K has to be in a waiting state, right? So the waiting of K is true. That is the second condition. Now let's look at the third condition. The third condition is K is not equal to I. Okay, so the process that received the probe here, the process K, should not be the initiator of the probe. Okay, so if it were the initiator of the probe, that means we have already detected deadlock, which is going to be a part of the second statement that we're going to look at in a few minutes. So if K is not equal to I, so this is the probe received by an intermediate process, which is not the initiator process. Okay, so if K is not equal to I, has to be true. And finally, the depend of K comma I is not true. Okay, so so the process I does not depend on process K for its progress. Okay, so when all four of these conditions are true, when all four of these conditions are met, then what does the process K do? It's going to send a probe on all its outgoing edges. Okay, so it's going to send the probe by changing the sender and the receiver values. Okay, so the sender is going to be the process K itself now. The initiator is not going to change. The initiator is going to remain the process I, and then the receiving process is going to change. So the receiving process is going to be the process it has been the probe has been sent to. Okay, so there is a new probe sent on each outgoing edge to each process J or each successor J. Okay, and then the depend of K comma I is set to true. All right, so when all these conditions are true, the process K is going to forward the probe on in order to find out if there is a deadlock in the system. All right, so now let's take a look at the second statement of the algorithm. So if a probe is received by a process K, right, and waiting of K is true, and if K is in a waiting state, right, and K is equal to I, right, that means the receiving process is the same as the initiator process of the probe. So the process that initiated the probe received that probe again. All right, so basically the probe went around in a cycle and it came back to the initiator. So this means that the process K deadlocked. Okay, so this is the algorithm to detect a resource deadlock. So let's look at some of the observations we can make from the resource deadlock detection algorithm. So to detect a deadlock, the initiator must be in a cycle. So when the probe was sent out by the initiator, it was finally received by the initiator in order to determine that a deadlock exists. Okay, so the message complexity of this algorithm is is of the order of E. So the message complexity of this algorithm is of the order of the number of edges of the wait for graph. So another name for this algorithm is called the edge chasing algorithm. Now let's look at a communication deadlock scenario. All right. So the figure given has a resource deadlock, but it does not have a communication deadlock. So if you remember, a resource deadlock happens because a process is waiting on resources from a set of other processes, right? And it has to receive those resources from all the processes in order to proceed. However, in communication deadlock, that is different. So if a process is waiting on a set of processes, if at least one of the processes in the set gives an okay for the waiting process to go forward, it can move forward. All right. So the process 3, which is waiting for a set of processes 1, 4 and 5 in order to proceed, can receive a signal from any one of the processes 1, 4 and 5 in order to break the deadlock and come out of the deadlock. So there is no communication deadlock in the given figure, but there is an existing resource deadlock. Finally, let's take a look at the algorithm for detection of a communication deadlock. So, so let's look at the algorithm. So a process which is not in a waiting state, okay? So if a process is not waiting for any other process, it's going to ignore any probe that is received as a part of the communication deadlock detection algorithm, okay? If not, what happens? So if it is the first probe, Okay, so if one of the waiting processes receives a probe for the very first time, it's going to mark the sender of the probe as its parent, and it's going to forward the probe to all its successors. All right, so basically it's going to forward the probe to all the outgoing channels, right? To all the outgoing channels, to all the processes on its outgoing channels. Okay. Now, what happens if this is not the first probe? If this was not the first probe, then it will simply send an acknowledgement to the sender indicating that it received a probe. Okay. Now, what happens when the sender process receives an acknowledgement from every successor? Okay. So basically a sender that sent out a probe on each of its outgoing channels also receives an acknowledgement from each of those outgoing channels is going to send the acknowledgement up to its parent. Okay, so now the communication deadlock is detected if the initiator receives the acknowledgement. Okay, so if you remember, resource deadlock is detected if there is a cycle in the system, right? So communication deadlock is detected when a tree is grown all the way uh, uh, deep, and then it receives an acknowledgements back up, okay, to the root of the tree, and that is how a communication deadlock is detected. If you notice carefully, this algorithm is very similar to the Dijkstra-Scholten termination detection algorithm that we looked at the beginning of today's lecture. Okay, so there are several similarities between this algorithm and the Dijkstra-Scholten algorithm. So this is the end of today's lecture. Please email me with any questions that you have, or if you have any questions, come by during the office hours or during one of the lab hours, and we can discuss your qualms and queries during that time. So I hope the lecture is gonna make good sense, most of it, and I look forward to answering any questions that you have via email or in person whenever possible. Okay, have a good day.